University of South Florida. Our host.
It's working?
All good here.
Okay, go ahead. You're set.
So, hi, my name is Charles Mentzer from the University of South Florida, here to present the work in phase evolution in VZT from atomistic simulations. I would like to thank the U.S. Department of Energy and the National Science Foundation for supporting this work. We're interested in ferroelectric reactors because they exhibit excellent ferroelectric, piezoelectric, and piezoelectric properties and find numerous applications in capacitors, nonlinear optical devices, and common rail fuel injection systems. And we're specifically interested in VZT as it is a standout, as it is lead-free, as an extremely rich phase diagram, as well as being highly tunable with a concentration of zirconium. Here we have the experimental dependence of the transitional temperature on the concentration of zirconium with temperature in Kelvin. And with the inset being the entire temperature range, it's important to show the inset as after about 40% of zirconium, the polarization of the cell is essentially zero, so we transition to using the maximum and the dielectric constant to determine where the phase transition is occurring. And we can see in the experimental data that around 10% a pinched phase transition occurs. So at around 10%, the pinched phase transition occurs, and while this is well understood experimentally, there's a lack of a microscopic understanding for why this phenomenon occurs. Also, the associated peak of the dielectric susceptibility for barium for VZT is much broader than BTL, which is sometimes referred to as the diffuse phase transition, which is also something that we would like to investigate. With our motivations in set, we can move forward to establish our goals. The first is to develop a first principle-based computational approach able to model this alloy in a wide compositional and temperature range. And the second is to apply this computational approach along with some first principle insights from zero Kelvin simulations to recreate accurately these phase evolutions of VZT, as well as answer some of the previous asked questions. So the first thing that has to be done is first principle DFT calculations at 0 Kelvin, and then to use the insights that we gain from the 0 Kelvin simulations to then modify the effective Hamiltonian to extend it to finite temperatures. Here we have the two main insights that we gain from our 0 Kelvin simulations. The first is the chemical pressure that's induced. Here we have the both cubic and ground state after we've already done a substitution of titanium for zirconium. It's important to show both the cubic and ground state because this inside of the chemical pressure will happen regardless of the phase or the temperature. And the chemical pressure here is being shown with the green arrows showing out as the substitution for zirconium induces a negative chemical pressure due to a larger atomic size of zirconium. The second major insight that we found from the 0 Kelvin simulations is an electrostatic effect. In figure A, we have the pure barium titanate where the green arrows are showcasing the forces that are acting on the cell. And in figure B, we have, once we've made a substitution for zirconium, not only does zirconium itself not contribute to the collective distortion of the cell, but it also weakens the cell. This interestingly creates two competing effects, as the chemical pressure, as a negative chemical pressure, is ferroelectrically favorable, while the weakening of the collective distortion is ferroelectrically unfavorable. So we use to study the finite temperature simulations, we use the effective Hamiltonian approach, where the basic Hamiltonian is shown here. For the effect of the negative chemical pressure, we use the hydrostatic pressure P, which is shown here. And then for the electrostatic effect, we added in a restoring force into the effective Hamiltonian, and then used that effective Hamiltonian as the framework for the molecular dynamic code to study the finite temperature properties for VZT. The simulation supercell of 30 by 30 by 30 was used, and it was annealed from 450 Kelvin to 10 Kelvin in steps of 10 Kelvin, where at each temperature step, 100,000 MD steps were used. Here we have a couple representatives for the dependence of polarization on temperature. For pure barium titanate, or X is equal to 0, we have 3 clear phase transitions going from paraelectric cubic to ferroelectric just going to the phase changes, yeah. At 8%, we have the 3 phases that move closer to each other. And we can see that not only do the phases move closer to each other, but the general polarization of the cell is reduced. This is expected and does match well with the experimental findings. At 14%, we see that there's a pinch phase transition where it goes straight from the paraelectric cubic to the ferroelectric longitudinal. And then at 20%, we showcase this as we find evidence for a slightly monoclinic phase. And this will be investigated later on in the presentation. So here we have a comparison between the dependence of the transition temperatures on the concentration of zirconium, comparing the simulation and the experimental. We find excellent agreement between the computational and the experimental data, which leads us to conclude that the mechanical electrostatic effects that were discovered from the 0 Kelvin simulations are primarily responsible for the phase evolution in VZT and these standards of tolerance. And here you can see that we continue to use the yellow triangles for the transition to using the maximum dielectric constant. So to gain some further insights into the phase evolution of VZT, as well as to investigate the origin of the monoclinic phase, we looked at the dipole patterns. At 14%, we see almost completely homogeneous cell. But at 18 and 20%, we do see some polar nanoregions of cylindrical shape, and this does explain the monoclinic phases that we identified earlier. At 30%, the polar nanoregion grows in size significantly, until at 40%, the cell is completely disordered, signaling a lack of polarization. Oh, and these cells are all at 150 Kelvin. So we also wanted to investigate the nature of the diffuse phase transition, which for VZT occurs around 15 to 20%. It is suggested to originate due to the overlap of the maximum and the dielectric constants, although the exact nature of the phenomenon is unknown. So to investigate this, we took VZT at a concentration of 18% and applied an AC electric field at 1 gigahertz to it along 3 different directions of the 100, the 110, and the 111. And we used a temperature range of 280 to 380 Kelvin, as this nicely surrounds the Curie point of VZT of 350 Kelvin. And a supercell size of 30 by 30 by 30 is continued to be used. So here we have the dependence of the polarization on the applied electric field for 280 Kelvin and 320 Kelvin, where purple corresponds to the 100, green corresponds to the 110, and blue corresponds to the 111. As can be seen, all 3 ferroelectric phases are stable, which is a manifestation of the free energies being very close to each other. Interestingly, this occurs for the entire temperature range for this concentration that we investigated. And such phase coexistence signals could explain the associated diffuse nature and phase transition of of this material. So in conclusion, we found that the substitution for zirconium for titanium leads to a negative chemical pressure, which is ferroelectrically favorable, as well as a weakening of the collective distortion of the cell, which is ferroelectrically unfavorable. Using these two effects in our computational data with the modification of the effective Hamiltonian, we were able to accurately recreate the phase transitions of BZT, which concludes us to that they are the primary factors for that phase evolution, as well as in the region of the diffuse phase transition, any one of the three ferroelectric phases are stable and could conclude that those are the result of the diffuse phase transition. We believe that our study advances the understanding of ferroelectric relaxes without nominal charge, and that our proposed methodology allows for further investigations, for many investigations into such solid solutions. Thank you.
Thank you. Do you have any questions? Okay, I guess I'll ask a question. So, if I understand what you're doing, you're starting with the effective Hamiltonian model, which has some sort of vector degree of freedom associated with each cell, plus you have things like form effective charges. Is that correct? Is that the sort of model you're starting with for the zirconium titanium alloys? In other words, before you do your thing with the chemical pressure and the electrostatic pressure, if I understood what you were saying. Maybe I've got the wrong.
So that's the part of the research that I did not contribute to, the actual foundations.
Okay.
The foundation before the 0 Kelvin simulations were done.
Okay.
So I'm actually not sure the answer to that.
Okay. Yes, question back there.
I'm Steve Tidrow from Alfred University. Normally, as an experimentalist, I look at barium zirconate as being cubic, and I would do a Bouguere's law between barium zirconate and barium titanate to find the TC. Does anyone, so this is really more of a general question to the entire audience, why the solid solution between barium zirconate and barium titanate behaves so extraordinarily different than many other solid solutions?
Anybody in the audience want to answer that?
No, that's